That's right. So that the universe we see around us really is hyperdimensional, but we can't see it because these other dimensions have curled up. They're too small to be observed.
What if the universe we see is just a shadow of something far greater? The James Webb Space Telescope has captured anomalies in the Abell 2744 galaxy cluster, light diffraction patterns that shouldn't exist. These aren't imaging errors. They defy known physics. Google's quantum AI team ran the data through their most advanced algorithms. The results? Mathematical structures eerily consistent with string theory's predictions of higher dimensions.
And perhaps our universe is a membrane, in which case perhaps some of these dimensions could be large.
For the first time, we may be seeing not just deep space, but deep reality. Something is bending the rules, and it might not be from our universe. Did the James Webb Telescope just spot a hidden dimension?
Astronomers have captured some of the most detailed images ever seen of the galaxies in deep space.
The James Webb Space Telescope may have just captured evidence of something that shouldn't exist, a hidden dimension. In a recent deep space scan of the Abell 2744 galaxy cluster, Webb's infrared cameras detected bizarre light diffraction patterns. These weren't normal distortions. These anomalies broke the rules, the very physics our universe is built on. At first, scientists thought it might be noise or image artifacts. But what came next changed everything. Google's quantum AI team took those images and ran them through cutting-edge quantum algorithms. These tools are built to uncover patterns too complex for classical computers. The results? They found precise, consistent mathematical signatures that matched predictions from string theory, the leading framework suggesting the existence of extra dimensions. These weren't random blips. These were the exact kinds of patterns that physicists have long believed might appear if higher dimensions were interacting with our own. That means what the Webb telescope saw might not just be light behaving strangely. It could be a window into dimensions we've never seen before. Think about that. Other dimensions, subtly influencing the observable universe, now possibly captured in real telescope data.
NASA's newest telescope is giving us a look at the very beginnings of that universe.
The team published their preliminary findings last month. Since then, the physics community has been buzzing. While it's not confirmed proof yet, it's serious enough that researchers around the world are diving into the data. If these findings hold up under scrutiny, this could be one of the most important discoveries in the history of physics. It challenges everything, from the nature of space and time to how the universe was formed. Skeptics point out that it could be a misunderstood astrophysical phenomenon or an unknown interaction with dark matter. But here's the catch. These patterns line up too closely with what string theory says we'd find if extra dimensions were real. JWST's dimensional clues. The James Webb Space Telescope, JWST, has just given us a glimpse into the early universe, and what it found could change physics forever. 3 galaxies, captured as they appeared just 400 to 600 million years after the Big Bang, have sparked a wave of excitement. But it's not just their age that's blowing minds. It's what researchers found inside the data that's truly groundbreaking.
The mysteries of the world and some great news for a while. It has been likened to the greatest scientific discoveries of all time.
This isn't just another deep space discovery. What sets this apart is the way the data was analyzed. For the first time, a research team used quantum computing algorithms to process JWST images, specifically those showing strange radiation patterns that don't behave the way we expect. These patterns aren't just visual curiosities. Hidden inside them are mathematical signatures, signals buried in the cosmic background radiation that may match predictions made by string theorists for decades. Yes, we're talking about higher dimensions. Let's break it down. JWST is orbiting roughly 1 million miles from Earth, acting as our most powerful cosmic observatory. It captures light that has traveled billions of years to reach us. Now, thanks to quantum computing, scientists can analyze that light with a level of precision never before possible. And what they've found might be our first observational hint of dimensions beyond the 3 we experience.
We spend all our life in 3 dimensions. We go forward, backward, left, right, up, down.
The research team didn't just run the images through a standard filter. Using advanced quantum algorithms, they were able to isolate anomalies, patterns that traditional computing might have completely missed. These aren't random glitches or noise. They're mathematically consistent and match certain predictions from theoretical models involving multidimensional physics. The focus of this deep dive is a region of space known as Abell 2744, a galaxy cluster also called Pandora's cluster. It's a chaotic region, packed with gravitational lensing and overlapping light signatures. But it's in this cosmic chaos that the team found strange light diffraction patterns, subtle distortions that don't match any known explanation within standard models.
We can measure the amount of stars in the galaxy. We know the size because we know how far away it is.
Could this be proof of extra dimensions? Are we witnessing evidence of the universe's hidden structure? The researchers are not jumping to conclusions, but they are paying close attention. Every data point is being rechecked, every pattern reevaluated. But if these findings hold up under peer review, we might be looking at the first real step toward validating theories that until now have lived only on chalkboards and in math-heavy journals. Hidden dimensions detected. The James Webb Space Telescope, JWST, wasn't designed to find hidden dimensions, but it might be doing just that. Its mission? To peer deeper into the universe than ever before, and that's exactly what it's doing.
And in this way, the James Webb Space Telescope looks through all of that.
Recently, JWST zoomed in on a mysterious region of space called Pandora's cluster, also known as Abell 2744. What it found there is now sending shockwaves through the world of astrophysics. In this one small patch of the sky, researchers spotted two of the most distant galaxies ever recorded, nearly 33 billion light-years away. Confirmed by a team from Penn State, this discovery gives us a rare glimpse into the early universe and the possible conditions that birthed the first galaxies. But it's not just about distance, it's about what else was hiding in the data. JWST is different from previous telescopes like Hubble. With its powerful infrared technology, Webb can see through thick clouds of cosmic dust to capture high-resolution images of galaxies we've never seen before. When scientists pointed it at Pandora's cluster, the results were breathtaking. But then, something unexpected happened. It wasn't astronomers who first noticed the strange patterns in the data. It was Google's quantum computing team. Using powerful quantum algorithms, they processed the images from JWST and uncovered something ordinary software couldn't detect: bizarre light distortion patterns that don't fit any known models of physics. These distortions showed up as subtle anomalies in the infrared spectrum, tiny glitches that suggest something unusual was happening at a quantum level. On one side of the screen, you can see what traditional physics says should happen. On the other, you can see what JWST actually captured.
A pair of galaxies that are merging together, interacting, you can see that they're disturbed.
The mismatch has experts buzzing. Could these patterns be signs of extra dimensions? That's the big question. The story doesn't stop there. When Google's team applied their analysis to other galaxy clusters, they found the same strange patterns, again and again. And here's where it gets really wild. Those patterns perfectly matched predictions from theoretical models of higher dimensional space. Some physicists are calling this the most important discovery since Einstein's theory of relativity. If true, it could reshape our entire understanding of space, time, and the universe itself. Cosmic light unveiled. The James Webb Space Telescope, JWST, has once again stunned astronomers and cosmologists by capturing light from two ancient galaxies whose photons have journeyed across the cosmos for more than 13.2 billion years. This remarkable feat means that we are observing these galaxies as they were when the universe was a mere 330 million years old, just a blink in cosmic time following the Big Bang. But here's where the science gets even more compelling. Due to the continued expansion of the universe, those very galaxies, though we observe them as they once were, are no longer in that primordial location. In fact, the fabric of space has stretched so dramatically over the past 13 billion years that these galaxies are now estimated to lie about 33 billion light-years from us. This extraordinary observation underscores the relativistic principle that while light moves at a constant speed, the space it travels through is dynamic and expanding. Penn State astrophysicist Joel Leja likens these distant galaxies to cosmic lighthouses, an analogy that elegantly captures their significance. Just like terrestrial lighthouses pierce through dense fog to warn or guide ships, these ancient galaxies shone their light through the early universe's thin veil of neutral hydrogen gas, what cosmologists refer to as the cosmic fog. This fog gradually cleared during a period known as ionization, and light from galaxies like these helped drive that transformation. These galaxies, acting as beacons across time, illuminate not only their immediate surroundings, but also the evolving structure and chemistry of the early cosmos. Their light carries encoded messages, spectral fingerprints, about the temperature, composition, and density of the universe mere hundreds of millions of years after its birth.
Even the sun's heat would blind the telescope to the faint infrared signals from space.
What truly surprised researchers, however, is the size of these galaxies. One of them spans about 2,000 light-years across, a considerable scale given the expectations for such early structures. For comparison, our Milky Way stretches roughly 100,000 light-years, but galaxies in the infant universe were expected to be small, irregular, and chaotic. The discovery of a relatively large, structured galaxy this early suggests that galaxy formation may have progressed faster and more efficiently than standard models predict. Adding another layer of intrigue, Google's quantum computing lab has introduced a theoretical curveball. Using quantum algorithms to analyze light patterns from these and other deep-field images, their team claims to have found subtle anomalies, fluctuations in the light spectrum that don't align with predictions based on known physical laws.
A Hubble image of the same thing that James Webb photographed. I'll bring in the Hubble image and we can see the change.
These patterns, according to researchers, may hint at the influence of hidden dimensions, a possibility long proposed by string theory. To explore this, scientists turn to gravitational lensing, particularly in clusters like Abell 2744. This massive cluster distorts space-time with its intense gravity, bending and magnifying light from galaxies far beyond it. Through this lensing effect, we see even deeper into the past, some galaxies as they existed more than 12 billion years ago. If the observed distortions in light patterns persist after careful analysis, they could be the first observational evidence supporting string theory's assertion that our universe contains up to 10 dimensions, only 4 of which, 3 spatial and 1 temporal, we can directly perceive. Physicists like Dr. Lisa Randall have long theorized that gravity may be the one fundamental force capable of leaking into these extra dimensions. If true, this leakage might cause minute but detectable deviations in gravitational or quantum behavior, potentially the exact kind of patterns that quantum computing tools are just beginning to unveil. In sum, with the combined power of JWST and cutting-edge quantum analysis, we may be closer than ever to glimpsing the hidden architecture of the universe, one lighthouse at a time. Quantum universe. Secrets. For years, astronomers and physicists studied cosmic data using conventional computing tools. Everything looked familiar, predictable even. But now, thanks to quantum analysis techniques, strange new patterns are emerging from the same data. These patterns weren't created recently. They've been hiding in plain sight all along. So what changed? The tools. Researchers have discovered unexpected chemical signatures in distant galaxies, indications that these galaxies became chemically enriched far earlier than anyone expected. This isn't just a small surprise. If elements like carbon and oxygen formed faster than predicted, it could mean the building blocks for planets, and even life, were around much sooner in the universe's history. That single discovery has ripple effects across multiple fields. Some theoretical physicists believe these odd patterns might be signs of quantum effects from the very early universe.
About what that first billion years of the universe was like, to having it in crisp, high definition.
Effects that can't be explained by our current models. This opens the door to a bigger possibility. Maybe we need an entirely new framework for understanding the universe. Now here's where things get even more interesting. Those same patterns might actually point to something much bigger. Extra dimensions, not science fiction, actual additional dimensions of space beyond the ones we can see. If these truly exist, They could explain some of science's biggest mysteries, like why gravity is so weak compared to other forces, or what dark matter and dark energy actually are. Think about it. What if gravity isn't weak, but instead is being pulled into other dimensions we can't detect directly? That could explain why dark matter and dark energy make up about 95% of our universe's mass energy and yet remain invisible. This discovery could finally bridge the gap between the two major theories, quantum mechanics and general relativity. Scientists have been trying to connect them for nearly a century without success. Major institutions like MIT, Caltech, and Princeton aren't waiting around. Their teams are building new simulations, reanalyzing James Webb Telescope data, and planning focused observations on regions that showed these anomalies. They're trying to figure out how light would behave if it really were interacting with extra dimensions. But science always needs a second look. Some experts suggest these patterns might be glitches, possibly caused by the telescope's instruments or the way data is processed.
The elevator pitch for the Webb telescope was to get the baby pictures of the universe.
Others say the quantum effects themselves may not require any extra dimensions at all. Still, the signals are there, and the questions they raise could change everything we know about space, time, and the structure of the universe. Hidden dimensions revealing themselves. Something strange is happening, and it's not a glitch. Scientists across different labs and tools are seeing the same quiet disturbance in reality. At first, it looked like noise, small errors, but the more they dig, the clearer it gets. Across satellite data, space telescopes, and quantum computers, a single pattern keeps repeating, not once, not twice, over and over. At Princeton, a team ran simulations on how particles would behave if extra dimensions were real and close enough to interact. The equations didn't predict chaos. They pointed to tiny, unpredictable shifts in gravity, not enough to tip your coffee, but enough to matter. They didn't stop there. They checked satellite data, those ultra-sensitive ones that track Earth's gravitational field. The numbers showed tiny anomalies, almost nothing, but not random, the same kind of disturbance that their equations predicted. That got their attention. Then came the Webb Space Telescope, a completely different machine, but it picked up a similar pattern in deep space readings.
The Webb has already studied the atmospheres of dozens of distant planets.
And when Google's quantum computers were run through unrelated problems, the same type of signal showed up again. These systems weren't supposed to connect, but they did. It's as if something is pushing from the outside, not hard, not obvious, but enough to tug, enough to leave marks, again and again. Cosmologist David Strauss says scientists know their own bias is a risk. Many of them want to find something new, something big. That's why they now do blinded studies, where they don't see the results until the end. It's a way to stay honest. But even with those safeguards, the strange data keeps returning. And with every test, it looks less like a fluke. The more they run the numbers, the less noise there is. Patterns sharpen. It's like watching static slowly turn into a picture. Something's out there. Not fiction, not fantasy. This is math. This is a measurement. And here's what keeps some scientists up at night. What if these strange patterns aren't just signs? What if they're warnings? What if reality isn't smooth but layered, and something in another layer is getting closer? If these anomalies are signs of extra dimensions, what happens when that wall finally breaks? What's on the other side? What if we were never supposed to see these patterns? What if the universe isn't meant to be fully known, but something hidden is starting to show? The scratches are growing. The curtain is shifting. What's watching us? Something strange is happening, and it's not a glitch. Scientists across different labs and tools are seeing the same quiet disturbance in reality. At first, it looked like noise, small errors, but the more they dig, the clearer it gets. Across satellite data, space telescopes, and quantum computers, a single pattern keeps repeating. Not once, not twice, over and over. At Princeton, a team ran simulations on how particles would behave if extra dimensions were real and close enough to interact. The equations didn't predict chaos. They pointed to tiny, unpredictable shifts in gravity, not enough to tip your coffee, but enough to matter. They didn't stop there. They checked satellite data, those ultra-sensitive ones that track Earth's gravitational field. The numbers showed tiny anomalies, almost nothing, but not random, the same kind of disturbance that their equations predicted. That got their attention. Then came the Webb Space Telescope, a completely different machine, but it picked up a similar pattern in deep space readings. And when Google's quantum computers were run through unrelated problems, the same type of signal showed up again.
Isolated from the rest of the universe is a quantum computer.
These systems weren't supposed to connect, but they did. It's as if something is pushing from the outside. Not hard, not obvious, but enough to tug, enough to leave marks, again and again. Cosmologist David Strauss says scientists know their own bias is a risk. Many of them want to find something new, something big. That's why they now do blinded studies, where they don't see the results until the end. It's a way to stay honest. But even with those safeguards, the strange data keeps returning. And with every test, it looks less like a fluke. The more they run the numbers, the less noise there is. Patterns sharpen. It's like watching static slowly turn into a picture. Something's out there. Not fiction, not fantasy. This is math. This is a measurement. Beyond what's visible. Some physicists now believe there might be extra dimensions, hidden layers of space folded up right next to us. They're not glowing, spinning, or obvious. They're invisible, quiet, and for a while, many thought they were harmless, just background noise in the structure of reality. But lately, that belief is starting to crack. A few scientists are wondering, what if gravity isn't weak? It's leaking. What if energy is slipping away into another dimension? And if that's happening, what else might be leaking through? Here's the unsettling idea. If these hidden dimensions are touching ours, then we might not just be observers in the universe. We could be connected to something else. And if we're connected, maybe something is watching us back. Sounds impossible? So did flight, splitting the atom, and landing on the moon. But those ideas only sounded impossible, until they weren't. Now, we're standing at the edge of a discovery bigger than anyone expected. The question isn't whether these extra dimensions exist. The real question is, what's next? For decades, we've built massive telescopes, powerful colliders, and fast computers, all to see farther and dig deeper.
To me, one of the most profound impacts of the Webb telescope is the observations of exoplanets.
But what if the answer was never far away? What if it's been right here, in the folds between everything, waiting? That's why scientists aren't looking away. At research centers like Maroro, they're chasing every clue. The James Webb Space Telescope spotted strange patterns in space, signals that don't match known physics. Then Google's quantum computing team ran their own tests and found something shocking. Those patterns match the math for extra dimensions. Now, everything's moving fast. Observation missions are already locked in. Scientists are aiming their instruments at the regions where those strange signals first appeared. This time, they're using different setups, more precision, better tools. Peer review usually takes a year. Not this time. Journals are rushing. Everyone wants answers. And the key will be verification. If other telescopes with different technologies see the same thing, it changes everything. That would be hard to ignore. Suddenly, our world isn't just three-dimensional. It's part of a much bigger picture. This discovery could explain why gravity is weak. It might unlock the secrets of dark matter, maybe even reveal the source of dark energy. More evidence backing JWST's findings. While the James Webb Space Telescope, JWST, has provided unprecedented insights into the early universe,
the Webb Telescope is created by some of the brightest minds in the world, and all of them are going to be watching at the edge of their seat.
The concept of extra dimensions is supported by a broader array of astronomical and scientific evidence beyond JWST's findings. Various theoretical frameworks and observational studies contribute to this intriguing possibility. String theory posits that the fundamental constituents of the universe are one-dimensional strings rather than point-like particles. This theory inherently requires additional spatial dimensions, beyond the familiar three, to be mathematically consistent. Specifically, superstring theory necessitates 10 dimensions, while M-theory extends this to 11. These extra dimensions are hypothesized to be compactified or curled up at scales beyond current detection capabilities. Gravitational lensing, the bending of light by massive objects, offers a potential avenue to detect extra dimensions. Theoretical studies suggest that in models with extra dimensions, the deflection angle of light could exhibit energy-dependent deviations from predictions made by general relativity. Observations of light bending near massive celestial bodies, such as black holes, could thus provide indirect evidence for the existence of additional dimensions. Research indicates that if extra dimensions exist, they could influence the behavior of black holes. For instance, light bending near the supermassive black hole at the center of our galaxy might appear brighter than expected in a universe with extra dimensions. Detecting such anomalies in brightness could serve as evidence supporting theories that incorporate extra dimensions. High-energy particle colliders, the Large Hadron Collider, LHC, have been instrumental in probing the existence of extra dimensions. Certain models predict that collisions at these energies could produce microscopic black holes or other phenomena indicative of extra dimensions. While such events have not been observed, the absence of evidence places constraints on the size and properties of these hypothesized dimensions. The theory of cosmic inflation, which describes the rapid expansion of the universe shortly after the Big Bang, may also be connected to extra dimensions.
What exactly did the Webb telescope find in the early universe, and why scientists believe this is the end of the Big Bang theory?
Some models suggest that the inflaton field, responsible for driving inflation, could be influenced by the geometry of higher dimensional space. Analyzing patterns in the cosmic microwave background radiation and large-scale structure of the universe could thus provide insights into the role of extra dimensions in cosmic evolution. While direct evidence for extra dimensions remains elusive, a combination of theoretical models and observational studies across various domains of physics and astronomy continues to explore this possibility. Advancements in technology and observational techniques may eventually provide the necessary data to confirm or refute the existence of dimensions beyond our current perception. We hope you enjoyed this video. Stay tuned for more.